Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and today we will speak about classification and regression trees, specifically about how to predict with a card. You should understand the basic structure of a tree model. You should also understand that the basic idea of a tree model is the same for classification and regression. You should understand how the label of a new observation is predicted via a card, and finally, you should know the hypothesis space of card. Cards are binary trees. Well, there are different cards which are not binary, but in this lecture, at 99.9% of the time, we will speak about binary trees. Binary trees represent a top-down hierarchy with binary splits. What does that mean? Top-down means that we go from top to bottom, of course, and we start with a root node, which we call here A. And then the data in this root node is divided binary into two other nodes, here called B and C. And this is a binary split. And then two things can happen. Either this is the last split here, then as for C, this is a terminal node, also called leaf. So these leaves are not split further, or we have an internal node B, and internal nodes are split further. So we go further to the bottom and split B into D and E, and then we split D into F and G, and E into H and I. So in the end, we end up with 5 leaves or terminal nodes, C, F, G, H, and I. We can also talk about nodes with respect to their relative relationships. They can either be parent nodes or child nodes. A parent node has always 2 child nodes in a binary tree, and we speak about left child and right child. The root node itself does not have any parents, and leaves do not have any children. As said before, trees can be used as well for classification as for regression. First, we will speak a little bit about classification trees, and then we will speak about regression trees. So here you see a classification tree, which also uses the structure of a binary tree. So it's also constructed top-down with binary splits in a data-optimal way. What this data-optimal way means will be explained in a later chunk. For now, we just accept that we already have those data-optimal splits, and we can think about how this tree works after the learning process. Each split is a threshold decision for a single feature. What does that mean? Let's have a look at the first node, the root node, and at what's below this root node box. There it says sepal length smaller 5.5, and on the left hand side is a yes, and on the right hand side is a no. So this means first that we are speaking about the iris dataset, which has 4 features, as you might know, and one of those 4 features is the sepal length. Another feature what we use here is the sepal width. And now if an observation has a feature value of sepal length smaller than 5.5, so if the answer to that question here is yes, then it goes to the left child. If the answer is no, then it goes to the right child. Okay, and this goes on and on. So let's say we went to the left child, and then we look at sepal width. And if sepal width is larger or equal than 2.8, we go to the left hand side, and if it's smaller than 2.8, we go to the right hand side. And we can do this for all those nodes, the exact same thing. And then we end up in the leaves at some point. And now I would like to explain you what those numbers in those leaves, or actually in all the nodes, tell us. So let's have a look at the left leaf here, just as an example. In the middle of this node, we have three numbers, 0.98, 0.02, and 0.00, and these add up to 1. And that's not by chance. So if you look at all the other nodes, and don't have to be leaf nodes, in all these nodes, numbers add up to 1. This means that we look here at the distribution of the classes. So the iris dataset is a multi-class classification task with 3 classes, setosa, versicolor, and virginica. So we have 3 classes, and these 3 numbers just tell us the relative frequency of those 3 classes in the data point corresponding to this leaf or to this node. Okay? So this means that in this node here on the bottom left, almost all the data points are from class setosa, which is why the hard label prediction here is setosa. If you look at the other nodes, for example, that one here on the right bottom side, the largest class is the 3rd class, which is virginica. And if we look at, for example, this leaf here, the largest class is the 2nd class, which is versicolor. So the second line tells us which classes these data points in that node belong to. And the class name on the top of the leaf or of the node is the constant prediction, so the hard label prediction. And then we have another number. This is here 30% in the last row, and this tells us how many data points of the entire data set are in that node. So if you look at the root node, then you will see there are 100% of the data points in the root node. Of course, we start with the root node. If we then sum up the left and the right child of the root node, that's 35 and 65%, these adds up to 1. If we then further split here, then those 35% here are split into 30% and 5%. So this is the relative frequency or the proportion of the entire data set and not of the binary split here. Okay, I guess that's it for the structure of this classification tree. Let's have a look at what happens if we predict a new data point. So in this case, sepal length is 5 and sepal width is 3, which means we have this data point here. If we pass this data point through the tree, then the first decision is that sepal length is smaller than 5.5. So this is a yes, so we go to the left child. And the next question is sepal width larger or equal than 2.8. And since this is 3, it's also a yes, so we end up in that leaf. And the constant prediction is setosa in that case. This means also that each observation is assigned to exactly one leaf, so there's no ambiguity here. A classification tree can make a hard label prediction, as in this case setosa, but we can also predict probabilities, or let's say probability scores, which are here 0.98, 0.02, and 0.0. We can also look at this from a slightly different perspective, and we have this on the right hand side in this plot here. We visualize the tree structure here a bit differently. Let's try to understand what happens here. The first split is with respect to sepal length smaller 5.5. So what we have here is that we split at 5.5 for sepal length. Then if we go to yes, so smaller than 5.5, then we split with respect to sepal width at 2.8. Okay, but this split goes only until we reach sepal length equals 5.5. Okay, it does not go further. If we now go on the right hand side of sepal length 5.5, then we split again using z-par length, in that case at 6.2. So we have another vertical line here. And then here we are finished. So this is one entire leaf. But if we are between 5.5 and 6.2, we split again with respect to z-par width, equaling 3.1. Okay. So this means that we have now a partition with 5 parts, and these 5 parts correspond to one of the leaf nodes. Okay, so we have 1, 2, 3, 4, 5, and now we can distribute those numbers here. Let's see if I get it right on the first try. That's a 5, that's easy. So the 1 would be that one here. So then that's 3, that's 2, and that's 4. Okay. We can also have a slightly different look at this if we think of a rule-based model. So it's the same tree as on the last slides, but now we have a table here which tells us a little bit how these leaves, so we have again 5 leaves, are constructed. So that's the same label distributions as you've seen before, and now we can also say, okay, what features does an observation have to have so that it ends up in this leaf node? And the answer is the z-par width has to be larger or equal than 2.8, and the z-par length has to be smaller than 5.5. And that's, of course, exactly the same thing here. So these 2.8 correspond to this node, and these 5.5 correspond to this node, or to this splits, to these splits, let's say. And if we look at the Virginica node here, it's in node 5 in this numbering, which is of course that one. Z-par width does not matter at all because we split 2 times with respect to z-par length. So as long as z-par length is larger or equal than 6.2, we end up in the 5th leaf, giving us a prediction of of Virginica. Now I've told you before that we can use trees for regressions as well. And basically the idea is exactly the same as for classification. The only difference is the predictions in leaves or terminal nodes are a numerical scalar and not a distribution of classes or a hard label class. So we have here an example of one continuous feature and one continuous target. So we have a regression task here, and the points are the data points. And we can look at what happens here. So the question is X larger or equal than 1.9? And if the answer is no, let's do this first, then we go to the right-hand side, which means we are left from 1.9 here. And the number here, the first number in that leaf, tells us the constant prediction, which is 1.8. Okay, so this value here is 1.8, which is kind of the best prediction we can make looking at these data points here. Okay, this will basically be the mean, the empirical mean of those data points, but we will see that later. And then we can go also to the right-hand side and split several times at 4.7, at 6.4, and have always a constant prediction. So for example, in this case here, for the data points larger than 6.4, we have prediction of minus 0.74. Trees are basically an additive model. So let's look at first formula, I guess, in the card chapter. The hypothesis space consists of these functions here. So it's the sum of the constant prediction Cm times an indicator function. And this indicator function tells us if the data point X we're trying to predict is in some set Q, and Qm is always a rectangle in trees. So As you've seen before, this is a rectangle, this is a rectangle, this is a rectangle, and so on. Okay, we have 5 rectangles here, and we just have to look, or first we have to find out in which rectangle is the observation. Let's say, for example, rectangle 5, and then we have to look at the constant prediction in that rectangle. And the constant prediction can be either the class distribution of Setosa, Virginica, and Versicolor, or just the class label hard prediction. In that case, what was it? Virginica. Or in the case of regression, we basically also have rectangles, but since we only have one feature here, those rectangles are just intervals. Okay, and in each interval we have one constant prediction. So we have C1, C2, C3, and C4. We can also visualize this for a two-dimensional regression example. So we have a feature x2, we have a feature x1, and the target y, which is numerical. And then you see that the function that we look at here is also the step function. Okay, so we have now rectangles in x1 and x2 dimension, and in each rectangle we have just a constant prediction, a constant numerical value. If we have a binary classification with probabilities, then we can also plot such a two-dimensional surface, and it looks very similar, but then of course the probabilities have to be something between 0 and 1.